Science and religion. Can science tell you how the world works? How you got here? Does it have all the answers for all the fundamental questions? What, why, when, how did you get here? Or does religion have all the answers? Is there a conflict between the two, or are they compatible? Does one need the other, or is the science in itself enough to explain everything? Well, religions then, there are several different religions, and so one could argue, I guess, that they can't all be right, or can they? Because they all seem to have the same ideology, that there's something that exists over and above the physical, and over and above oneself. Someone, perhaps, that is even looking after you. So if you then say that there are different religions and they have different practices, but basically the same ideology, then perhaps we can say that that they are all right, rather than all wrong. And is there another dimension other than the physical? Well, there's a non-physical. We know that. There's your mind, but is there a spiritual domain as well as the physical domain? Well, experiment done at University of Laurentian University in Sudbury, Canada, Ontario. He took students, and unbeknownst to what the experiment was about, he put helmets on them. Started off with hockey helmets, and put magnets on the helmets to measure the brain waves. Then he put them in an isolation booth, devoid of any ambient electromagnetic radiation, and of course, without the sense of sight, sound, or touch. And he monitored the brain waves. And he found that the left brain was shut down, and the right brain was more active. Then he took them out and asked them what they had experienced, and 4 out of 5 said that they had out-of-body experiences. They saw tunnels of white light. They felt someone was beside them or behind them. They even saw demonic creatures. And some even said they saw God, and therefore it's been nicknamed the God helmet. Now, that sort of indicates that there's something beyond the physical, something that is transcends the physical. And there's been documented cases, lots of cases, near-death experiences, even when the doctors have declared the patient's dead. And they've come back and they have had out-of-body experiences similar to what students have had in the experiment. And they had saw tunnels of white light. And they felt exaltation. They felt exalted. There was one case where a young cyclist, Australian, was cycling up the mountains. He was trying out for the Olympics. And he was hit by a large vehicle and wiped out the whole left part of his body. So he had to go through several operations, maybe as many as 10. And he had several out-of-body experiences. And he didn't want to come back because it felt so good. He was in no pain. So is there another domain other than the purely physical, or? Well, as I say, this is what religions really say. And even going back in history, we would maybe think of them as superstitious beliefs, but they had the same belief. For instance, Columbus sailed the ocean blue 1492, came to the Americas, and he found that they wouldn't give him any food, and his crew was starving. And the Indians believe that even inanimate objects have spirits. So Columbus said that their spirits or gods were angry at them, and to show their anger, they would gobble up the moon in 4 days. And when there was a lunar eclipse in 4 days, Columbus got his food. Now, I've heard that. I haven't double-checked to see if it's true or not, but it sounds pretty good. And I guess it depends on how dogmatic or how how fundamental the religion is. Because some religions, the most fundamental, think that all the other religions are wrong, and theirs is the only true religion. The most dogmatic would be the Islamic State. Well, they say anyone who doesn't follow their practices are infidels and should be eliminated. And if you want to stay in the state, if you acknowledge Abraham, you're allowed to leave. But otherwise, you have to convert. Otherwise, you could be beheaded, or if you're a woman under 40, it could be sold into slavery. Now, if you think I'm kidding, then a journalist, I think her name was Sullivan, went over to Iraq and interviewed a Islamic State prisoner, and that's exactly what he said. And some of the states that are headed up by the head of the religion, a theocracy, if you say anything against their leader or Muhammad, then you could have a price put on your head. So, but most of the religions now are fairly tolerant of other religions. In the Christian religion, there's an ecumenical movement where even though they may not practice the same, they have this. They say that their similarities are more than their differences. And going to the Far East, the Zen Buddhists, they want to divorce themselves from the physical by transcendental meditation. We do it in the West, TM. And by the way, your brain waves do change when you do TM. So, and there's a whole host of people then that don't necessarily follow a particular religion, but they believe in spirituality. There's something bigger than themselves. Okay. So, can science explain all that? Well, for science to be a scientific fact or a true theory or a law, you have to have evidence, or you have to be able to observe, and you have to be able to bring it back into the lab and test it out, and have it corroborated by another lab and another person. And I don't think science has done that. They really can't explain definitively, at least, and see actually what's happening. Now, of course, they can go through, and the brain is a very complex thing, so most complex thing in the universe. But still, it seems that the left brain looks after the physical part, and the right brain looks after the mental or spiritual part. And science tends to break things down. It's reductionistic. And the components and how they relate to each other. For instance, you, physically, are made of 65%, and I'm not sure if that's actually correct, but mostly 65%, say, water. And water is made up of the 3 atoms, 2 hydrogen and 1 oxygen, H2O. You have other atoms too, like carbon, which is important, combined with atoms of other elements in itself to form big molecules, and those are useful for you and for all complex life. But your atom is composed of negatively charged electrons, surrounded a nucleus, which is composed of protons and neutrons. But the size of the nucleus is to the size of the atom, as a speck of dust is to the size of a football stadium. So you're virtually all space. You're 99.9999999% space. Virtually nothing at all. So what's stopping you from falling through the floor? Because the atoms in the floor are 99.9999999% space as well. I mean, gravity's holding you on the ground, stopping the Chinese from falling off. Well, why don't you just keep falling down through the earth then? Are you a magician? Well, maybe you are, because you can levitate 1 angstrom unit, 10 to the minus 10 meters above the floor, above the ground. You don't actually touch it at all. You don't touch anything. You don't touch the wall. But what's really keeping you then from going through the floor? Well, the electrons in your atoms are negatively charged. And the electrons in the atoms in the floor are negatively charged. Like charges repel. So that's what's stopping you from going through the floor, or walking through the wall, or pushing your finger through your arm. What do we call that force? We call it the electromagnetic force. Let the force be with you. Now you are made up of mostly hydrogen. Over 50% of your atoms are hydrogen. Very dynamic, because they used to use it in airships in the Hindenburg, and it blew up. Hydrogen has 1 electron, 1 proton, and is the lightest element. So now they have to use helium, the second lightest element, with 2 with 2 protons, 2 neutrons, and 2 electrons. Most of the elements have the same number of protons and neutrons and electrons. Hydrogen being the only exception. But again, if you're in that room and you can't fall through the floor, and if no one can see you because you're basically all space. Maybe you can't be heard, or you can't be seen, or don't get so angry you want to blow up. Because if you release your hydrogen, you'll blow yourself up and everybody else in the room. So please, if you get angry, hold on to your hydrogen. But your protons and neutrons can be broken down more. Besides getting angry sometimes, you may have your days where nothing seems to be going right. You have your ups and your downs. Some days you feel up, some days you feel somewhat depressed, down. Physically, you're all up and down. You're made up of up and down quarks. Now, an up quark has a charge of 2 plus 2/3. And a down quark has a charge of minus 1/3. So 2 up and 1 down, that's plus 1 2/3, plus 2/3, minus 1/3, or 1. And a neutron has 2 down and 1 up. Minus 1/3, minus 1/3, plus 2/3, or 0. But many of your atoms have several protons. Now, if ever, then not necessarily in the room, but had days where nothing seems to be going right. Everything seems to be falling apart. No matter what you do, it doesn't seem to matter. Can't seem to hold it together. Well, your protons are positively charged, and you may have several of them, other than hydrogen, in the same atom. And positively charged items repel. So why aren't you flying apart? Why aren't your atoms flying apart? Because they have positively charged protons. What is holding you together? Well, there must be a charge then stronger than the electromagnetic charge. And what do we call that charge then? Or force? You call it a strong force. And that's what's holding your atoms together. All the protons and neutrons in the nucleus of your atoms. And that's what's holding you together and keeping you from flying apart. Let the force be with you. Now, I mentioned you're mostly hydrogen. Where'd you get all that hydrogen from? Mostly hydrogen atoms, at least. But before the mid 1920s, no one knew. But Hubble, looking through the largest telescope on Earth at the Mount Wilson Observatory in Los Angeles, he saw all the stars were going away from the Earth. How did you know that? Well, if the stars are going away as well, that means that what's that mean? It means the universe or space is expanding. And seeing how fast it expands and extrapolating back, you can see that it took 13.8 billion years for it to reach its current stage. Going back in time, when time was equal to 0. Well, how can time ever be 0? And what is the before time? We'll come back to that, because science does not have the answer. First, how did Hubble know that the stars were going away? Well, the stars give off light, and light is both a wave and a particle, a photon. To see it's a wave, all you have to do is hold up 2 fingers close together, look through it, and you'll see lines in between, faint lines, called, interference lines, where the waves interfere with each other. That's the same as when you throw 2 rocks in a pool, the waves will interfere with each other. And Newton, back in the 1600s, he saw that when you pass light through a prism, it breaks up into the colors of the rainbow, of the spectrum, from red up to indigo, indigo being like dark purple. And that each one of those colors has a different wavelength. That's the distance between 2 crests of a wave. And if the wavelength is larger, then it can't go up and down in the same length as frequently as when the wavelength is shorter. So if the wavelength is large, the frequency is lower, and when the wavelength is small, the frequency is higher. Now, sound is also propagated by waves. So you hear a train coming towards you, and the waves are being squashed together. The train's pushing them together. And so the frequency, the wavelength is smaller, and the frequency is higher. When the train goes by you, it pulls the waves apart, and the waves are therefore, the wavelength is larger, and the frequency is lower. So you hear it go from a high pitch or high frequency to a low pitch or frequency. And the sound drops. It's called the Doppler effect. Same thing happens with light then, because it's transmitted by waves. So if it's coming towards you, you see the high frequency or the indigo, and if it's going away from you, you see the low frequency, or the large wavelength, and it drops, goes towards the red. So it's going from a high frequency to a low frequency, from the indigo to the red. It's called a red shift. So that's how we knew that the stars, the light from the stars, was going away. You use a spectroscope to look at it, and you can see each color has a signature, so you can see that is the case. But going back then, if it's expanding and it's coming from a smaller and smaller space, then we go back to, say, the size of an atom. the whole universe and all the forces, everything. And math. When you divide by a smaller and smaller number, until you try to divide by 0, and all hell breaks loose. Math breaks down. It's called a singularity. Because when you try to add anything to infinity, you get infinity. You multiply by 3 times infinity, you get infinity. Infinity times infinity is infinity. So math breaks down. Well, time equals 0, that's also a singularity. And time equals, when you break down, divide by 0, as I say, you get infinity. So do you get infinity at time equals 0 then? And therefore, do you need something infinite to create the finite, something that has time equals 0? Now, Planck, back in the early 20th century, he said that time is discontinuous. You look at, take 1 billion years, take a million, divide it to 1 million years, to 100 years, to 10 years, to 1 year, to a month, to a week, to a day, to an hour, to a minute, to a second, to a microsecond, to a nanosecond, until you get down to 10 to the minus 43 seconds. And you can divide no longer as discontinuous. He called it a quanta. It's a quanta of time. We now call it a Planck time in his honor. And it is the time light takes to travel 1 Planck length. 1.6 times 10 to the minus 35 meters. So then if you can't have time less than 1 Planck time, how can you get to time equals 0? So science does not only have the answers, it will never have the answer unless it comes up with a different theory, which is a different theory of how the world started. It doesn't have one right now. Can't go back to time equals 0, or never can, unless it can dispute Planck's theory, which everyone now believes. Now they say, and by the way, here's where religion can be able to help out here, because we usually say God has an infinite mind, and also they say there's between the first Planck time and 0, there is all the forces, the super forces, are all together, and of course, everyone says that God is omnipotent, all powerful. So maybe we can say then that rather than all hell breaking loose, like in math, maybe all heaven breaks loose. And science has no position to say anything different. It doesn't know what happens at time equals 0. I mean, it has some maybe speculation, but in order for science to be true, as I say, you have to have evidence, empirical evidence. You have to be able to see it happen, and so far I don't think anyone's taken it back to the lab and tested it out, and I don't think they've created another universe yet. If they haven't, no one's come back to talk about it. So it can't just be speculation, it has to have empirical fact to make it a true fact, or a true theory, or a true law. And if there's one piece of evidence that doesn't comply, then you can no longer call it a true fact, a true theory, or a true law. So at 1 Planck time, the force of gravity separates from the superforce. And at 10 to the minus 35, you get your electromagnetic force separating from the superforce. And also, at that time, you get a great expansion. The universe goes through tremendous inflation. We sort of know that because at that time the universe is very uniform and the surface would be very smooth. And when you inflate a balloon, for instance, that's what happens. The surface becomes very flat and smooth. It's not a proof, if you like, but it's sort of an indication. There's other reasons why they think the universe expanded at that time. Then at 10 to the minus 12 seconds, interesting enough, you get your electromagnetic force. That's the one that keeps you from falling through the floor. And you get another force called the weak force, which we haven't mentioned yet. We've had the force of gravity, the strong force, the electromagnetic force, but there's also a weak force, the fourth force. You have some of that too. I mean, you're in that room, and maybe you can't be seen or heard. Maybe you can get bad, it will explode. But you do radiate. Not that much, though. It would take millions of years times the age of the universe for you to, your molecules or your atoms to radiate away using the weak force radioactive radiation. But it's still important because without it you may die. It protects you from the solar radiation and from cosmic radiation. Because what happens, it keeps the center of the Earth molten, and when the Earth rotates, you have a day, goes once around a day and every day, it sets up an electromagnetic field around the Earth, or shield. And that's what keeps the harmful solar radiation and harmful cosmic radiation coming down and hitting you, and perhaps killing you. It also protects the atmosphere from being blown away by solar radiation. And the atmosphere is very important. It has your oxygen, which you like to breathe. And it also mitigates all the stuff coming from outer space and coming down and hitting you. The meteorites, meteors, comets, and asteroids. It might not keep all of them through, and we'll talk about that later, but it does burn out most of them and makes most of them much smaller, so they're not as harmful. So let that force be with you. The other thing that happens at that time is a whole bunch of particles are created, and antiparticles. For every particle, there's an equal and oppositely charged antiparticle. For this electron, there's a positron. For an up quark, there's an anti-up quark. And so there's all those particles and antiparticles being created. And when they collide, they annihilate each other and form energy. Now here's where, you think a scientific fact is, well, it must be true, it's a scientific fact. Before 1905, every scientist that we know of believed that energy and matter are not the same. There's a law of conservation of energy, a law of conservation of matter or mass. Mass is the amount of material. Einstein said in 1905, no. You're wrong. They're the same. E equal mc squared. Your energy is equal to your mass, what material you have, times the speed of light, 10 to the 10 centimeters per second, times the speed of light. So again, if you're in that room, you will feel that you may want to explode. Hold on to your mass. Don't change energy. You blow yourself up, the other people in the room, the building, the city. That's how much energy you have. So hold on to it if you don't mind. And here's a case where then a so-called theory or fact was wrong, so they had to change it. Then at 10 to the minus 1, or 1/10 of a second, so you get your protons. But as I say, you have all those particles and antiparticles in the first second, and at the first second, then what happens? Something that scientists, again, cannot understand. But it is the reason why we have you here, and there's a universe. Because for every billion antiparticles, you get 1,000,000,001. I've also heard 100 million, 100 100 million. And that is extremely important for you and the universe. Because if there are particles and antiparticles, it would just be pure energy. And the universe and you would not exist. Science cannot explain that. Sorry. They try to take it back into the lab, and when they change mass into energy into mass, they always get equal number of particles and antiparticles. So this is another area where science doesn't know how you and everything else came about. Not only time equals 0, but time equals 1 second. But it's still so hot and so dense that everything can't come together. It takes another 308,000 years before it cools down enough. In that time, there's particles like photons, electrons, protons. But then at that time, the electron is captured by the proton. What do you got? One proton, one electron. What's that? Well, that's hydrogen. That's where you got all your hydrogen from. And you thought you're only less than 100 years old. No, more than half your atoms are 13.8 minus 308,000 years old. You're a lot older than you think. So what happens then? By the way, what we're talking about now is Boyle's law. It's not Boyle's law. It's a Big Bang Theory. And guess what? That name was given by someone who didn't believe in the Big Bang Theory. Hoyle. He had another theory about the universe. He called it steady state. There's a star being created, there's a star being disappears, and it's steady as she goes. There's no beginning, no end. It's just the way it is. But since Hubble saw that the universe was expanding, that theory is wrong. But he didn't like the other. He didn't like the other theory, so he called it a Big Bang, derisively, and the name stuck. So the name Big Bang was given by someone who doesn't believe in the Big Bang Theory. Now Hoyle, you can thank your lucky stars for Hoyle. You can't thank him for your hydrogen, because he still has a legacy, a good legacy. So just because you make one colossal mistake doesn't mean that everything you do is wrong either. So all these, and I say you should take things back into a lab and test it out. So how do they know? How do they test out the beginning of the universe? They can't really until they get to 10 to the minus 12 seconds, and which is where all their particles come from. So they do have a particle theory now, and they have taken it back to the lab and tested it out. Or try to define more closely what all the particles are. And they use a Large Hadron Collider in CERN in Switzerland. I can't say it. Switzerland. It consists of 23 miles or kilometers, I can't remember, loop under the ground, consisting of large electromagnetic magnets, where they accelerate particles in one direction near the speed of light, and particles in the other direction near the speed of light, smash them together. Just like within a car roller derby, you smash the cars together and the parts fly off. They had to see which parts the particles are made of. And they've come up, first they so many particles, they call it a particle zoo. Then they came up with a theory, a particle theory. Everything in the universe, including you, it consists of these particles and these forces. So every particle you ever want to know or ever is explained in this theory. I mentioned that you are up and down quarks. There's two other levels of up and down of quarks: the charm and the strange, and the top and the bottom. The last two pairs don't stick around too long, but you are all up and down quarks. And for every quark, there's a lepton, and the lepton for the up and down is an electron. The lepton for the other two pairs of quarks, I think it's the muon, and the tau. And then there's the four forces: the force of gravity, the strong force, the weak force, and the electromagnetic force. And for each one of those forces, there's a particle. And these particles exchange each other, and which makes the forces work. For instance, the electromagnetic boson is a light photon. So when you hold a north pole of one magnet up against the north pole of another magnet, or south poles, they resist coming together. Well, what's happening there? Exchange of photons. It's light that's keeping them apart. The boson for strong force is the gluon, and for the weak force is the W and Z boson, and for the gravity is the graviton. Now, there's also one guy called Higgs says we need one more boson to complete this particle theory. It gives mass to the other particles. He proposed that in the mid-20th century, and it was 2012 before they found this boson, and it's named the Higgs boson in his honor. And it took that long because they had to increase the power of the Large Hadron Collider before they got it. And when you predict something in a theory, and it comes true, then it gives that theory more credence. Now, they couldn't find the gravitons back then, because you need a collider about the size of the solar system. But they used another piece of equipment recently, and it's called the LIGO, L-I-G-O. It uses interference of waves. And fairly recently, they saw some gravitational waves. And that means there must be a graviton. Again, when that happens, it leads credence to their particle theory. They predicted it, and it came true. So as I say, you get your hydrogen at 380,000 years after the Big Bang. Also, let the photons release the photons as well, and you're still getting hit by the photons. Microwave background radiation. And when you listen to your AM radio or you look at TV with an aerial on it, you get 3% of the static is coming from that time. So you're still getting light from that particular time. It's very cool down to about 3 degrees above absolute zero, about minus 207 degrees. But nevertheless, you're still getting hit by photons from that. But what about all your other atoms? As I say, you can thank your lucky stars for those. You can't thank your lucky stars for hydrogen. But so, with all that hydrogen being released, in another half billion to billion years, it became so huge and so massive that the center became very, very, very hot. And if you recall, you can't really touch anything because there's space in between the nucleus and the circumference of an atom, because the electromagnetic force is greater than the force of gravity. But there was so much mass there, and so the force of gravity overcame the electromagnetic charge, and the protons touch each other in a process called fusion. Then created the next element in the periodic table, helium. 2 atoms, 2 protons, 2 neutrons, and 2 electrons, plus extra energy. Now, the hydrogen bomb is a fusion bomb, and that's what happens there. So they have all that extra energy given off. So that counteracts then the force of gravity trying to pull everything together. So you have a tug of war between the force of gravity and the force caused by the fusion. What do you got? Could say Judy Garland, but I'll say A Star Is Born. So that's where you get your star. What's the nearest star to you? Can you name it? Do you know its name? You should know. It's called the Sun. So the Sun is a star up there converting hydrogen into helium and giving off all energy in the form of warmth and light. But a star which is over 8 times more massive, when it uses up all the hydrogen, it'll fuse the helium together. And so on. When it uses up the helium, it'll fuse that together and get the next element. And so on until you get up to iron. But iron, which is a very much more heavier element, it has more, I forget how many, but more neutrons and protons. It doesn't give off energy, it requires energy. So there's nothing holding the force of gravity at bay. So it collapses almost instantaneously. Such force, it blows up into a supernova, and that gives off more energy, gives off more light than all the other stars in the galaxy combined. Could be 100 billion or 200 billion stars. So that is enough energy to fuse together the iron molecules, iron atoms, or elements, and all the other atoms heavier. Most of the other heavier atoms. Heavier elements. But it leaves behind a core. A core with all the space squashed out. Very heavy. 1 teaspoon of that would be more massive than all of the cars in North America. Now I tried to test that out, but when I take 1 teaspoon of it and try to put it in my hand, it falls right through. We call this electromagnetic force that stops anything from going through my hand, or my hand going through anything. But the force of gravity is so great, it goes right through my hand, right through the earth. And I did give up counting, to be truthful, I gave up counting the cars after the first 100 or so, that's all. So we have all that material being, including the atoms under, less heavier than iron, and those are more heavier. And when you have a star which is 100 times or more massive than our sun. When it explodes, it leaves behind a black hole. The black hole is so massive that even light cannot escape, and that's why it's black. Escape velocity of a black hole is greater than the speed of light. And now they figure that to create the most heaviest, or the heaviest elements, then you need either two neutron stars or two black holes to collide. So you had a lot of your other atoms being created then, even in the core of a star or from a supernova. And what happens to all that stuff that's then spewed into space? Well, gravity takes over and creates a second generation star. Our star, our sun, is a third or fourth generation. And they figure it was created 4.6 billion years ago. And by the way, 10 years ago, scientists were saying that the universe is 13.7 billion years, and the age of the solar system is 4.5 billion years. So they must have found another scientific fact to create a new scientific fact, incorporate it. So, get all your other atoms between 13.8 minus 308,000 years and 4.6 billion years. So you could have one carbon atom in one finger from a particular star in a particular galaxy in a particular and a carbon in the same finger, another finger from a different solar system, a different star in a different solar system in a different galaxy. A lot of steps, a lot of things happen to make you before you could get here. So we see where you got all what you're made of, all your atoms. Some 13.8 minus 308,000 years, and others you could have got a carbon atom, say 12 billion years old, and another carbon atom 6 billion years old. But when did you first come alive? Well, as I say, the solar system was created 4.6 billion years ago. But it was still too hot for any life to exist. I mean, it was quite chaotic. All of the material was swirling around. The lighter elements would have made the sun, hydrogen. And then the other elements and material would have been swirling around. But a lot of things crashing together, bombarding, and some small particles like dust, the electrostatic charge would have brought them together. And then the bigger entities, gravity would have brought them together, bashed them up. Things would have been pulverizing each other, and then gravity building it up into bigger and bigger things, till you got all your planets. And now they figure there's more dwarf planets than there are planets. But they would have been hitting each other as well, and maybe pulverizing each other. They figure a large one, size of Mars, called Theta, hit the Earth at the right angle, 45 degrees, so it didn't bounce off, and it didn't pulverize it, but it knocked off a great deal of the Earth's crust, which circled all of the moon, circled all of the Earth, which formed the moon. Gravity brought it together, formed the moon. And at that time, the Earth would have been so molten, or very hot, and the moon would have been circling around very close to the Earth, and the material going around the moon as well. so that more material would have settled on the other side of the moon. That's why when you go around the moon, you notice that there's only just the one dark spot, a lava lake. Whereas on this side, there's several, because the Earth's crust on the other moon's crust on the other side is much thicker, some 25 kilometers or miles, I forget. And then this side, and so the lava would have come up through the cracks in the crust on this side of the moon and formed more lava lakes. That's why you get the man in the moon, or if you think that's too sexist, you can say there's a man and a female kissing. You look from the top to the bottom. Maybe that's why it's so romantic. And the astronauts also brought back some rocks, which they think could only have been created in the Earth. And the Earth the moon is important for you. It stabilizes the Earth, and complex life like you could not probably exist or survive. But for the first 500 million years or so, then it was too hot for any life to really survive. And then life started, and again, science does not know exactly how it came about. It has some hypotheses, but it doesn't have any definitive theory or proof. It hasn't been able to create it in the lab. The best they could do, and they don't want to talk about it, is bring life back together by sewing together parts of things that were once dead and adding a bit of lightning. They don't like to talk about that or about what they actually do when they come up with all these drugs. Are they down in caves and mixing it up their potion, their magic potions, like the witches in Macbeth, adding eyes and newts and so on? Again, but this thing that they created, the scientists created, was a monster. It went around terrorizing everybody. And those of you that are not from this planet, you realize I'm talking about the scientist is Frankenstein. And that's not it is a sci-fi rather than a true scientist. But they've tried to create life in the lab. They come up with, say, amino acids, which are important or building block of life. But they haven't actually seen it happen or be able to create it. Now they have some hypotheses where they say you need these types of molecules, and then that would give you life. Now life is also found on Earth, but it's also found deep in the oceans. There are animals down there, probably created by chemical processes, where the volcanoes give off chemicals and create animals. But on Earth, there's plants and animals, and it's a symbiotic relationship really between them. At first, they were just then the very dull life, single atoms, single cells of life. And they reproduce by just splitting themselves, cloning themselves. And then, of course, you got multi-celled life. But the life then came up from the oceans onto the Earth, and you have a symbiotic relationship then between plants and animals. The plants took oxygen from the air, and through a process called photosynthesis, created their sugars or their food, their growth, and gave off carbon dioxide. Animals took in the carbon, took in the oxygen, and through a process I'll mention just shortly, gave off Oxygen. So, and they also gave back some of the carbon dioxide when they rotted, when they died and rotted. Now, how animals then, at least after I should ask you, and it's kind of embarrassing, but when did you first have sex? Well, the kind of sex we're talking about now, maybe 500 million years ago. And what happens there, for animals at least, you get half of your genes from your biological mother, half from your biological father, and your genes are composed of cells. And your cells, the center of the cell, the core of the cell, is deoxyribonucleic acid, DNA. And that's like a ladder with rungs in between. It consists of 4 different chemicals. It's twisted, so they call it a double helix. And when you grow, it splits down the middle, the rungs down the middle, and you get a new half, either a left or right half that matches perfectly most of the time, billions and billions of times. Unless, of course, it doesn't. And we now know that radiation can interrupt that process. So some of your DNA on one side may be knocked out, and you'll get a new piece of DNA. And your DNA is responsible for all of your characteristics. Color of your eyes, color of your hair, size of your nose, etc., etc., how big it can get. So when your DNA changes, maybe from radiation, then your physical characteristics may change as well. And what do we call that process? We call it mutation. So you have then all on Earth, at least you have the plants and the animals. But there was one smart-ass plant. Wasn't satisfied like the rest of the plants on the ground. He wanted to get more sunlight so he could grow bigger. So he grew up, became a tree, so he could grab more of that precious sunlight. And when he died, he didn't rot for millions of years. He just lay there and squashed down and became coal. So back then, there would have been, before that, there would have been more, there was more oxygen than there is now. So insects who use tubes to breathe would have been much larger, because if the tube is larger, the oxygen, more oxygen could get through and not be absorbed by the tubes. So your centipedes could have been as large as crocodiles back then. But you've had lots of close calls. If you look at the age of the different ages of Earth, you see you have your Triassic, you have your Jurassic, you have Cambrian, and so on, and most of those changes are associated with tumultuous type of events. Some of which was almost wiped out your life. And there's 5 major ones. There's one 225 million years ago. Happened in Siberia, where I guess it became very hot because of probably volcanoes, and it lit the coal. So with all that burning, and it made 70% of all living things go extinct. 90% in the ocean, and the rest on the Earth. So after that time, then you had the age of the dinosaurs. 160 million years they ruled the Earth. And you, being a mammal, would have had to stay underground during the daytime, because you can live underground, because you're a mammal and you have hot-blooded, whereas reptiles, like dinosaurs, cannot. They can live, but they can't move around much. So in order for you to eat, you had to hide in the underground in the daytime and come out and eat at night. Otherwise, you would have been eaten by the dinosaurs during the daytime. And during that time, the continents of the Earth were all together. One continent called Pangaea. And then they split apart to form the continents more or less as we see them now. Still moving, but moving so slow we can't see them. Now, until mid last century, no one knew that. I mean, maybe they looked at the map and said, "Oh, that's strange. Look at South America and look at Africa. They fit together a bit." But they didn't put two and two together. It remained for a Wagner. And he not only speculated or hypothesized that the continents fit together like pieces of a crossword puzzle, but he also got the proof. He looked at the fossils of plants and animals on this side of the Atlantic and saw that they existed on the other side of the Atlantic, the same species, with the fossils of the plants and animals on that side. And nowhere else on any of the continents on Earth. It's the second thing he did there, rather than just fitting together like a crossword puzzle. Thirdly, he looked at the land formations and found that they started on one side of the Atlantic and continued on the other. Even sedimentary rock, which they have different layers and different thicknesses in the sedimentary rock, they matched up perfectly from one side, and to another side on the other side of the Atlantic, indicating they must have split at that point. Fourthly, he looked at fossils in the north and found that they could only have lived in the south when they were living. So the land itself must have moved from the south to the north. For all those reasons, then he surmised that the one big planet split up into one big continent split up into several. Was he heralded as the greatest geologist at his time, or scientist? Exactly the opposite. He was vilified. He was made the laughingstock of the geological and the scientific community. They discarded his evidence. They said it's too preposterous. They didn't even look at it. So science should follow the evidence, no matter where it leads. Not the opinions, even of prominent scientists. They have to look at the evidence and then make their theories accordingly. He died in Greenland looking for more evidence for his theory, and you can call it a theory, a true theory, because it has evidence to support it. Helping some people stranded in the snow. Walked off and never seen again, and didn't then know that his theory would be vindicated. He would be vindicated, and his theory would be accepted. So even scientists and a consensus of scientists can be wrong. So you should follow the evidence, not just the opinions. It remained for another couple decades for another scientist to show how it would work. The continents are on plates which move around on top of the magma, the layer underneath the crust, and that's why you get all the volcanic activity where the plates meet, and the also a lot of the volcanic activity, as I say, and earthquakes, and why you see the Himalayas, where India coming from Africa, smashed into Eurasia and formed the Himalayan islands. So a lot of your mountain formations are caused like that. But as I say, dinosaurs were ruling the Earth. But 65 million years ago, a great event happened. Now, I mentioned that the atmosphere is supposed to protect you from mitigate all these things from coming from outer space. And also, the other thing that happens is Jupiter, which is more massive than all the other planets combined, therefore has a greater attractiveness, force of gravity, will attract a lot of the meteors, comets, and asteroids before they come down and hit the Earth. But 65 million years ago, it let down its guard, let a whopper through. It even went through the Earth's atmosphere and landed in the Yucatan Peninsula in Mexico. And caused quite a stir. Lots of heat forced by the collision, burnt off a lot of vegetation, and knocked out a lot of the Earth into the space, which circled the Earth and blocked off the sun. So dinosaurs, which need the sun to move in the daytime, and also eat lots of vegetation, they became extinct. And you, as a mammal, were able then to come out, and you proliferated and took over all the niches that formerly were occupied by the dinosaurs. So the event that happened 65 million years ago was not so good for the dinosaurs, but it was fairly good for you. Another event happened 10 million years ago. You recall that all the continents had split up. South America and North America were separate. And then 10 million years ago, they came together. That changed the ocean currents and also changed the climate of Africa. And it was no longer able to support the number of trees it did before, and it had more grassland or savanna. So some of the people living in some of the animals in the trees said, I guess I'll come down, it's too crowded here, and I'll see how I can do on the grassland. And probably some radiation came down and at the time, and maybe modified their DNA. And the DNA is responsible for the physical characteristics. So those that had changed their physical characteristics so they could better survive on the grasslands, survived and passed on their DNA to their offspring. And they then rest is history. So you, in fact, are a mutant. And the number of events that happened for you to be here, quite astronomical. Your parents had to meet, and they had to produce you. So you're physically half of each of those. Your DNA, half of it comes from your biological mother, half from your biological father, and then their parents had to meet and produce them, and so you're 1/4 of their physical characteristics. And over 100 years, that would be 3 generations, 4 generations. Was it 16? So you're part of 16 other people. Or 1 million. What would it be? 16,000 or 160,000 different people you are made up of. And then, of course, you had to be on a planet. It's the Goldilocks planet. It's not too far from the sun. Otherwise, it would be ice on it, and you need water liquid water to live. Or too close, and the water would evaporate. So you're on a planet, one of, was it 7 now? right? That is in the Goldilocks position. Now, science has been trying to find other planets that may have life. And they've been able to now see that many of the stars do have planets. So they've been looking for planets that are in the Goldilocks position in their solar system. Now, a guy called Carl Sagan was one of the first people that took looking for life in outer space seriously. Look for signals that can only be produced by intelligent life. And he set up a search called SETI, Search for Extraterrestrial Intelligence. He was very interested in exploring space, and he wrote a documentary called Cosmos, which explains exactly a lot of the things we were talking about now. He also said that people are stardust, not to quibble, but all of you accept your hydrogen is stardust. And he coined the phrase pale blue dot for the Earth, because if you see the Earth in space, it's all dark, and there's a pale blue dot, blue because it's covered with water. And he said that's contains everything that's ever happened to humans and other things in history, as far as we're concerned. And it's like an organism, and if one part of the organism is not working properly, then it affects the whole thing. So that's what we should be very careful of, how we treat the Earth. They put on a gold plate with the location of Earth and sent it off as well with several different languages of people that on Earth, and sent it off in the Voyager satellite. There's two of them. So if anyone in the future found it, they'd at least know that we existed. The position of the Earth you can get by triangulating on quasars, and quasars are neutron stars that are flashing. And there's only a few of them around, so they can find out where the solar system and you exist. Person that was inspired by Carl Sagan, and he brought together all the different fields of science. Before that, they were all pretty well separated and didn't talk to each other, but to do the space exploration and actually form NASA and so on, you need all the different sciences working collaboratively together. So he was partially responsible for that. And as I say, Carl, he inspired Neil deGrasse Tyson, who's now gone on and narrates at least another version of Cosmos, 10 or more episodes. He's a guy that knows quite a bit about all the scientific phenomena. And then you've got all of your atoms other than your hydrogen from different solar systems and in different galaxies. And as I said before, you could have one atom from one particular solar system in one particular galaxy, and another atom from another one. So you could have one carbon atom, 12 billion years old, another 6 billion years old. Well, they're also finding that there may be life really in the solar system, because they're finding a lot of there's probably more dwarf planets than there are planets, and some of them contain ice. And under ice there could be liquid water. And also on the moons of the planets, some of them are covered with ice and may have liquid water below the ice. And although they're farther away from the sun, they keep warm from the moons, at least from the tidal forces from the main planet, so that they could be liquid water. So we may even have microbes or biological life in the solar system. Maybe there was life on Mars, but Mars having being smaller, the core would be not perhaps would have solidified and is no longer molten iron, and therefore it wouldn't have the atmosphere that we have on Earth. And also Mars being smaller, it wouldn't have as much gravity to hold on to the atmosphere. So looks like there was water on Mars, and there still is ice there. So there might have been, at one time, who knows, there might have been even life on Mars, but I have not found anything yet. So far, it's just us. And so all of your atoms then were produced over those different, almost 9 billion years, between 13.8 minus 380,000 and 4.5 billion years ago. And that's where you got all your atoms from, except your hydrogen. And then at 380,000 years after the Big Bang, you got your hydrogen. And then at 1 second, you had a 1 in a billion chance of making it through that one particle. And out of 100 billion antiparticles, over 100 billion antiparticles made it through that. And then in the first second, you got your force of gravity, keeps you on the ground. You got the force of electromagnetic force, which keeps you from going through the ground. And the strong force, which keeps you together, flying apart. And the weak force protects you from a lot of the radiation and harmful asteroids and so on coming from outer space. And then at time equals 0, you got a universe. As far as we know, that's the only universe. There's some hypothesis, you can't really call it a theory because there's no evidence to support it, that there's more than one universe. But no one has yet to produce one and come back and go to it and come back and talk about it. And you can't, it doesn't have any actually evidence. Maybe have a hypothesis, but that's about it. There's no evidence to support it. So it's quite miraculous that you're here, really. And a lot of these events that science cannot understand, and one of them, the beginning of the universe, if you can believe Planck, that they will never understand, because you can't go beyond one Planck time. So in one sense, you could say that science needs religion. It's complementary to religion, because science cannot answer those fundamental questions. Whereas religion, if you're a religion mind, bet you can. Now the other thing about your DNA is that before 1600, people didn't really know what your weight was. Your DNA gives you the boundaries, at least, for how much you can weigh, how big you're going to become, and so on. And so you're in that room, and as I say, no one maybe can see you because you're 99.9999999 space, and you don't radiate that much, and but you are attractive. You could say, no, I'm not that attractive. You may think I am when you look at from a distance, but the closer I get, you see my flaws, and in particular, I'm overweight. Grossly overweight. No. The closer you are, And the more you weigh, or the bigger you are, sorry, the more attractive you are. So Newton saw, back in the 1600s, he saw an apple fell down to the tree. Didn't hit him on the head, although some people said it did. It was outside his house in his orchard. And he said that's an attraction between the apple and the earth. He went on to produce a formula. He says it's proportional. If you like it, you can say it's equal to the mass of the apple, that's the amount of material in the apple, times the mass of the earth, divided by the difference center of gravity of the apple and the center of gravity of the earth squared. Basically, the center of the apple and the center of the earth squared. And what's that? Well, it's gravity. And your attraction then to that other person, the other person to you, is equal to his mass times your mass divided by the distance between the two of you squared. But again, it's not that much attraction. You're not that attractive, actually. But if you go outside and get something more massive, you're more attracted to a mountain, or the mountain to you, or the earth itself. So you slide something in between you and the earth instrument. I think we call it a scale. And you can measure the attraction between you and the center of the earth. It's equal to your mass times the mass of the earth divided by the difference between you and the center of the earth squared. And what do we call it? That's your weight. So you want to gain weight, go down into a mine, and the distance there is less, therefore dividing by that, you would gain weight. Or you want to lose weight, go up onto a mountain, so the distance there is higher, so you should weigh less. Go to the center of go to the equator, and the Earth is not quite round, it bulges a bit at the equator, so you should weigh less at the equator than you do at the poles. But again, you probably couldn't measure it. Wouldn't be enough to measure. It would be negligible. Because if you compare, they say, the Earth to a billiard ball, and the surface of the Earth would be like the surface of a billiard ball. Not that much difference to measure. But if you really want to lose weight, go to the moon. The moon is only 1.2% as massive as the Earth. So you'd only weigh 1/6 as much on the moon. And even taking into consideration that the distance to the center of the moon is much less. So if you really want to smash some Olympic records, like pole vault or high jump, you should go to the moon. And your DNA also puts a limit on how high you can come. It's one of the factors. Nutrition is probably another one, but if you're like 2 meters tall, you may want to appear to be less, because that's 6'11" sort of thing. Like Isner, he's a great tennis player, and the height there is an advantage because he can serve much faster. He's got one of the fastest serves. Same with Veronica, he's only 6'5". So what you can do then is, if you want to appear to be closer, say it's closer to 6 feet, or less, measure yourself in larger units. So rather than be 2 meters tall, you could say you're 2/1000ths of a kilometer or kilometer high. Now if you're shorter and you want to appear to be a little taller, measure yourself in smaller units. So if you're just 1 meter and you want to be taller, Say that you're 100 centimeters tall, or 1,000 millimeters tall, or 1.6 times 10 to the 35 Planck lengths. Now you're in that room then, and you want to ask somebody how they are. You want to know how they are at that, when you ask them. But you'll never know, because you only see them as they were billions and trillions and quadrillions of Planck times ago, when the light comes from them to meet you. And the light travels at 10 to the 10th centimeters per second. When Armstrong, and you only see the moon as it was 1.2 seconds ago. So Armstrong, when he communicated with Houston, there was always a delay because it took 1.2 seconds for the radio waves, which are part of the electromagnetic spectrum, like light, to get there, and then another 1.2 seconds to get back. And you don't see the sun as it is now. You see it as it was 9 or 8 minutes ago. And you don't see the stars as they are now, but as they were thousands of years ago. And galaxies as they were millions of years ago. And the farthest star away that we have seen through the Hubble telescope is 13 billion light years away. Sorry, the light takes 13 billion years. So, and when we get into those distances, then we use the time that light takes as part of a distance. For instance, we say that the moon is 1.2 light seconds away. The sun is 8 or 9 light minutes away. And the farthest star that we've seen is 13 billion light years away. So, basically then, do you believe in ghosts? You should. Go and look at a star, and you may just be seeing the ghost of the star, because the star could have already died, and the light is still coming towards you. So you're not seeing the star, you're seeing the ghost of the star. So you can travel, if you like, or at least look into the past. Time travel. Because light takes that long for you to get here. Now, Newton, of course, he said that gravity is the attraction between the Earth and you. It's a force of gravity, so that's the force he defined. He also said that everything keeps going unless someone stops it. Aristotle didn't say that before, 2,000 years ago. He said everything stops. You need the hand of God to keep it going. Newton says no. With my two laws, I can show you that first is how the moon goes around the Earth. Take a cannonball and a cannon up on a mountain, drop the cannonball, it drops down to the ground, just like the apple, to the ground below. But shoot the cannonball out of the cannon, and it goes a mile, a kilometer, or a kilometer, before it falls down. Shoot it harder, it'll go halfway around the Earth, and then shoot it hard again, go all the way around. or shoot it harder again, it'll go around and keep going around. And it keeps going because there's nothing there to stop it, except some little friction, not much. And it's the force of gravity. It's the same, and the law of momentum. But I might have, when I said that you're attracted to an attractive person, I might have misled you. But again, I think I misled you when I said that you were attractive. What really happens is a person falls for you. You create a space, you change the space around you like a wall around you, and the other person falls into that wall. So, and here's where I can be a little sexist again. Women have in the past fallen for every man that they met. And they'll fall for every man that they meet in the future. And we call them fallen women, right? But to be fair, men have fallen for every female that they ever met, and will fall for every female that they ever will meet. But they also fall for men as well. What happens to the women create a well around them, change the space around them, and you fall into that space. Like when you go on a trampoline, you form a well or an indentation in the trampoline, place a basketball on it, and the basketball falls into you. The closer it gets, the harder it falls. So you're not really attractive. You change the space. And the attraction or the gravity or the force of gravity is a warp in space-time. It's not like Newton said, attraction between any two objects. To get an idea, he came up with that with a thought experiment, and to get an idea of what he's talking about there. What's he talking about? Space is changing? Isn't it always the same? No. You have a rubber sheet representing space-time. Space and time are so interrelated. We'll just talk about space for the moment. And you have two ball bearings, one larger than the other. The large one representing the Earth, and the smaller one representing the Moon. And you roll the smaller ball bearing towards the larger ball bearing, and depending on how massive the two objects are, and how fast you throw it, and how close it comes, the two come together, it'll either go way on by, or it'll hit the well, in case of the ball bearing, and be deflected and go on. Or in the case of the Moon, it'll be deflected and go on. Or it'll hit the well or the warp and go right around the other ball bearing. Or the Moon will go around the Earth. Not because of the attraction of the Moon towards the Earth. The mass of the Earth has changed the space around it and warped it so that the Moon falls into that warp and goes around. That's Newton's general theory of relativity. Now, again, people who examine that said, well, that doesn't make sense. And it was, to be truthful, just a hypothesis because there wasn't any empirical evidence. And they said, well, the consensus of opinion is that, it's wrong. So what did Newton say? What did Einstein say? All you need is one person or one scientist with one piece of evidence that doesn't comply with this theory or hypothesis, and that's the truth that's wrong. In other words, your opinion doesn't really matter. You need the evidence before you can call it wrong. And you should take it back in the lab and perform an experiment to find that evidence. So when that happened, and the equipment that they used was a solar system, during a solar eclipse, they looked at the stars behind the sun and they found that they had been misplaced because the photons had gone through the warp caused by the mass of the moon and had been deflected. So the stars appeared in a different location. And Einstein became very famous. Now he also said that time changes as well when you come towards a large mass. It slows down. But these laws then replaced Newton's laws. Was Newton's laws wrong? Yes or no? Because we still use Newton's law for a lot of everyday practices. They're much easier to work out. It's good enough to land men on the moon and to make satellites go faster by using the gravity of the planets to fling them farther into space than they could go under their own steam. But it isn't good enough. They aren't good enough to explain the rotation of Mercury around the sun. Mercury being close to the sun is more affected by the warp caused by the mass of the sun, and you need Einstein's equations to understand more definitively how Mercury goes around the sun. Again, you could say, well, who cares? I mean, it doesn't. What's that got to do with the price of rhubarb? Well, what about your GPS? Supposing you wanted to go someplace. Well, if you don't use Einstein's equations, your GPS would be out in 2 hours. Because time on the satellite runs faster than time on Earth. You need a atomic clock to measure it. But if you didn't incorporate that, because they use the GPS uses the satellites to come up with the distances, your GPS would be out in 2 hours. So the Einsteinian word is quite weird, isn't it? Where you go around changing your time and your space. Now time also varies the faster you go. The faster you go, the slower it goes. By the way, if you want to see in the future, you can. Now, what are you talking about? Time slows down? Here's another thought experiment then. You have a friend that's going on a trip, tell him to go on a tell him to go on a train actually. And when he gets, the train goes 100 miles an hour, tell him to throw the ball, go up the front and throw the ball 100 miles an hour in front of the train. Well, it'll go 200 miles per hour. They'll say, well, wait until the train goes 3/4 the speed of light. Then go up and throw it 3/4 the speed of light. How fast will it go then? It won't go 1.5 times the speed of light because the speed of light is constant. It's 10 to 10 centimeters per second. Something's got to give. Distance is equal to speed times time. D equal VT. Your velocity can't change because it can't go faster than the speed of light. So time has to go slower to compensate. So you want to time travel again? Well, as I say, you can go in the back. You can go back in time by looking and seeing stars from the past, or anything. You go back in time. But what if you in the future get into a rocket ship and travel near the speed of light, and depending on how fast you go and how long you go when you come back, the rest of the world would have aged. So you'll see the future in that sense. So the Einsteinian world then, and we can call it that because it is how things work on the macro level, and there's been no evidence to disprove it. All evidence complies. It's weird. It goes around changing space and time. Was he given a Nobel Prize for that? No. But he was given a Nobel Prize for how he helped out the other world vision, which is how the world works at the small quantum level. Quantum mechanics or quantum field theory. Got the Nobel Prize for the photoelectric effect, where if you hit light, light hits an atom, a photon of light, it'll give off an electron, the photoelectric effect. And that's why you don't get hit by an elevator door when you go through the door. Or the car doesn't come down and hit the car's door, doesn't come down and hit the car when the car goes through. And he didn't like the quantum theory or quantum world because it relies on probabilities. And he famously said, God does not play dice. He wanted to, and he spent the better part of his career trying to find out a theory of everything that combined the two. Quantum gravity takes gravity into effect in the quantum world. Normally you don't have to because in the quantum world because the masses are so small and the force of gravity is so weak you can get away without it, except when you can't, when the masses are very strong, like in a black hole or in the beginning of the universe. But the quantum theory is even weirder than Einstein's. The founders would be Planck, who said that both space and time are discontinuous, and Einstein's they are not. And Heisenberg said that if two things are related, the more certain you are about one, the less certain you can be about the other. For instance, if you want to know the speed of a particle definitively, then you can't know the position definitively. The more you know about the position, the less you'll know about the speed, and vice versa. Not because there's a problem with measurement, because that is the reality at the quantum level. Same with probabilities. I mean, everything can pop up here, there, everywhere. And it's only when you add all your probabilities together you get anything close to what we think is reality in our world. To show the weirdness, to the classic experiment, the two-slit experiment. Pass light to two slits and see what it appears on the opposite side of the wall, the opposite side. Well, you think you get two two lines. Photons of light go straight, right? No, you get several lines. Because light can be a wave, and the waves interfere with each other. Like I said, when you hold two fingers up, you can see the waves of light forming two lines, and lines in between, interference lines, like when you throw two rocks in a pool. That's weird enough. But when you look at it before it goes through, measure it or look at it, it changes just to have the two lines. So somehow the waves have changed back into a particle. Just by observation. And okay, suppose we pass one photon at a time then. And surely then, it'll either have to go through the left slit or the right slit. So you should get one or a left line and a right line over time. No. You get several lines, indicating that photon has interfered with itself or gone through both the slits at the same time. Okay, well, let's look at each photon as it goes through, before it goes through. And lo and behold, you get the two lines back again. Indicates a particle. So one of the founders, he made the mathematics simpler by putting vectors, I believe, in quantum mechanics. He said that anyone says they understand quantum mechanics doesn't understand quantum mechanics. And yet, it is the most powerful tool that the science has. Doesn't know why it works, but it predicts things to unprecedented accuracy, 23 decimal places. And there's no evidence to prove it wrong. So here you have two world theories about how everything works, and they're incompatible. As I say, Einstein tried to bring the two together to a theory of everything, or if you like, quantum gravity. And other people have been doing that too, physicists. He said, if we could do that, then maybe we would be closer to knowing the mind of God. Now there is some hypothesis that quarks can be even smaller and than they are, very small, and millions of times smaller, in strings. And strings will compose everything, including all of the forces as well. But that is just a hypothesis. I think it's much ado about nothing myself, because you can never measure them. They're so small. And apparently you need 10 dimensions before you can come up with a theory of everything using string theory. And so far, I don't think anyone has created another dimension. I'll come back to talk about it. But there are people working on it. It's very theoretical, of course, because you can't really have, it's not a theory, it's theoretical. They call it string theory. They should be calling it a string hypothesis. So, here's another thing that science doesn't understand. The other thing it doesn't understand is, why did we get all these constants and forces exactly the way they are? Because if some of them weren't exactly the way they are, if they were slightly changed, the universe couldn't exist. For instance, gravity. If it was a little more less strong, the force, it wouldn't have brought together all the hydrogen atoms, and the universe would just be all hydrogens, no stars, and hence not you. Or if it was any stronger, once it created the hydrogen, it would draw it back together, the force of gravity, into, say, a big crunch. The one they really don't understand is the cosmological constant. Lambert, Einstein put it in his general theory of relativity. He took it out because he said, well, I don't need it. It could explain how the universe expands or contracts. But he said, like everybody else, no, the universe is always constant. It's been there before, no beginning, no end, and always like it is. Like the steady state theory. He said it was a big mistake in his career. The biggest mistake was thinking it was a mistake, because it's now needed to explain how the universe expands. So they looked at it and said, well, okay, let's measure that, and let's hypothesize or theorize, take all the equations we know in science, and see what theoretically it should be, and then measure it and see what it actually is. And they were out by 10 to the 120th between the theoretical and the measurable. If it was what they theorized, everything would fall apart. All your atoms would fly apart and everything else. So, do they really know the fundamental questions about how the world works? No, and by the way, they figure the reason why, let's look at it, and they discovered that the universe is accelerating. I thought it would be contracting over time, getting cooler, going back into a big crunch. No, so they said, well, maybe space is not empty. It's full of virtual particles and antiparticles. And of course, as you get more space, you get more particles and antiparticles, and when they come together, they form energy, dark energy. And they need to explain things. They need to have that comprise of 70% of the universe. And they call it dark energy because they don't really know what it is. And also looking at gravity, they need about 4 or 5 times more gravity, or more mass then, to explain a certain phenomenon as well. When you look at a skater spin, they put their arms out, go slower, put their arms in, go faster, and Pluto, of course, goes slower around the sun than Mercury. But when they look at the star going around the center of the galaxy, not just our galaxy, but other galaxies too, it doesn't work. They need more mass, need more gravity. Need 4 or 5 times more. Don't know what it is, can't see it, so they call it dark matter. It doesn't consist of quarks or atoms. It doesn't react to any photoelectric signals like light or radar or X-rays. Could be WIMPs, weakly interactive particle systems. Weakly interactive massive particles. But they haven't found any, and they're looking for them in the Large Hadron Collider. But so far I've not found them. And so they're totally in the dark. So here you have what the scientists know is only 5% of what's going on. Because they're in the dark for 95%. And of that 5%, they don't know either what's going on because they have 2 different conflicting or incompatible theories. So if you rely on science to answer all the fundamental questions, you're out of luck. the other thing that I have a hard time explaining. Why can we get all these equations and all these laws and theories, eke them out of the universe? In other words, out of reality. Before 1905, we had the law of conservation of energy, law of conservation of matter, Newton's law of gravity, Newton's law of momentum, Charles' law, Bohr's law, and everything. And after 1905, we had Einstein's special theory of relativity, his general theory of relativity, and all the equations that come out of quantum mechanics and quantum field theory. What if the other way around? Rather than getting things from the universe is created from them, from the mind, or from the formulas, from the laws. And we do create virtual reality already. They have performers that have already died, giving a performance on stage, and they use holograms, and you don't know whether to clap for them, of course, because they're already dead. But we are creating virtual reality. Probably needs somebody a little more wise than us, omniscient, and maybe more powerful, omnipotent, and happening everywhere, omnipresent, before you could create the whole universe. But that's exactly what we think God is. So it looks like really science needs religion is to complement it. Not only is it compatible, it's complementary. The other thing is that what's happening nowadays is science is becoming so powerful, and that we need something to hold it accountable, because it can be used either for harmful purposes, either on purpose or without knowing it. And two areas that, and I'm going to put this on a separate video, but I'll just mention it now, is telecommunications and computers. Because it's becoming so powerful now that you can monitor everything that a human does. And control what they say and think if you want to. And there are people that are just doing just that. Some of it is unintentional, some of it is very intentional, to maintain the power and to find anyone that opposes you. And the other is, of course, genetic engineering. And we do it for plants, and we do it for animals, and we can do it for humans as well. You may say, oh, that's a good thing. We can eliminate a lot of the genetic diseases. But how far should you go? I mean, we're getting into group politics, and supposing a group wants to say, well, I think I not only want to control the thoughts of people through my telecommunications, but I want to make them look more like my group through biological or genetic engineering. And countries like China and definitely North Korea wouldn't think twice before they did. But as I say, I'll leave this video here and finish it then saying there are maybe two different views on how the world works, the scientific and the religious. And maybe they are complementary. For instance, you would say if for science, you can say, oh, it's all just accidents, fortuitous as they may be, random accidents, why you and everything else got here. Or you could say there is some design and purpose. For instance, you say, thank God, if something happens that could be deleterious if it doesn't. Or thank God that didn't happen. Or and you can't understand something, you can say, oh, God, I knows why that happens. Or God, I knows why that didn't happen. And thank God this happened, or thank God that didn't happen. Well, thank God that the force of gravity exists, because otherwise you'd fall off the earth. Thank God there's a electromagnetic force stronger than the force of gravity. Otherwise you'd go down, you and everything else would go down into the center of the earth, maybe into a black hole or a singularity. And God only knows what that is. And thank God that there's a strong force, otherwise you'd fly apart. And thank God there's a weak force, otherwise you would be hurt by harmful solar and cosmic radiation, and wouldn't have an atmosphere that could support you and mitigate against you being hit by all the debris in space. And thank God, of course, that all the other steps happen, many of which science cannot explain. For instance, why is there one extra particle that went on to create everything in the universe? And science does not know why. So there's a multitude of steps, all of which, if they didn't happen, you wouldn't be here. And science, it cannot explain them all. Some of the fundamental questions about how the universe came about, and you came about, how you got here, why you got here, so on. And there seems to be, and even in the fact that there seems to be another domain, the spiritual domain, it really doesn't have evidence to explain that. So I'm going to leave this video here, and I'm going to have another video on the possible harmful effects of not curbing use of science, and how religion may be the answer, because science needs a moral compass. Religion could provide that. Do unto others only as you have them do unto you. Bye for now.